Okay, yeah, hello everyone. Welcome to one more lecture of the course on processing in memory. The course is not on processing in memory, it's on computer architecture. But we continue today talking about processing in memory. I hope we are all set, and I hope that people in Zoom and YouTube can see the slides right now. If there is any issue, please let me know. So remember, yesterday we started to focus with a lot of detail on processing in memory. Why there is a need for processing in memory or for more data-centric computing systems, and we classified after the motivation. We classified the different processing in memory models into or approaches into two main ones. The first one is processing using memory, where we typically exploit analog operation of the memory cells in order to perform computation. And we saw very good examples of that, such as rowclone and Ambit, that we are going to very quickly review today. And we also talk about the other pillar of processing in memory these days that is called processing near memory. And that's what's going to take us like at least half of the lecture today. We are going to see what are those proposals where computation is not directly done with the memory cells, but is done using processing elements that reside near the memory arrays. So that's what the lecture today is about. We will finish with some discussion and also some works about how to enable processing in memory. We will discuss what are different things that still need to be changed in existing computing systems in order to enable processing in memory capabilities and make these systems more data-centric in the end. Feel free to stop me and ask any questions as they are needed. Remember the two ping approaches. We have already seen this slide in the previous lecture. We talk about two approaches to processing in memory. The first one is processing using memory. The second one is processing near memory. Yesterday, we focused mostly on processing using memory with DRAM, processing using DRAM, but we also mentioned that it's possible to do processing using memory with other memory technologies as well, such as SRAM or non-volatile memories. And in fact, we explain a couple, or at least briefly, we explain a couple of examples for phase change memory and also other types of non-volatile memories that can be leveraged to create a crossbar that computes dot product operations and matrix operations that can be useful for machine learning, neural networks, and these sort of applications, right? And these can be, in some sense, out of these any of these memory technologies. Today, we are going to talk about processing near memory. In processing near memory, we will start indeed with examples of logic layers in 3-stack memory. Remember that 3-stack memory is a technology that stacks multiple layers of DRAM on top of each other in order to increase the memory bandwidth, right? And these 3-stack memories typically have a logic layer where typically memory controllers reside, but also there is some extra area that can be used to place some compute elements, right? And that's what we are going to see in the different proposals with logic layers in 3D stack memory that we are going to cover today. Silicon interposers is something that I mentioned yesterday as well, when we have a 3D stack memory that is connected to some processor or some accelerator, for example, created with an Fpga. With the silicon interposer, we can have much wider connections between the memory, between the 3-stack memory and the processor, and this way have much larger bandwidth. This is the approach that is used these days by FPGAs and also by GPUs, or high-end GPUs at least. Today we will mention some other examples, such as logic in memory controllers. We are going to very briefly mention a couple of examples. Logic in memory chips is something that we have already seen as well near the bank, such as the Pei Micro Architecture, or proposals from Samsung and from SK Hynix. We will review them all today again. Logic in the modules, we have seen the AXTeam example. We will have one slide about it as well today. Near the caches, we are not really targeting this into this lecture, but yeah, there are also some proposals for placing computation near the caches, and that's indeed something not infrequent in real world as well. If you check the architecture of GPUs, NVIDIA and AMD GPUs, you will see that they have specialized units near the caches, either the scratchpad that is in each of the DPU cores, or the larger cache, typically L2 cache, that is shared across all the different GPU cores. And there you can find some units that are specialized for some computation, for example, atomic operations, right? That's something that indeed exists in real systems these days. And finally, we have also proposals that do logic or processing near or inside the storage device. And I mentioned yesterday Flash Cosmos. That's more like processing using memory, because in reality it's using the NAND flash cells in order to perform the computation. So it's more like processing using memory, but there are also many interesting approaches to placing processing elements near the storage and computing for those applications that require very, very large data sets, and probably they are not so, they don't have so much reuse, so that they can take advantage of the memory itself. Okay, yeah, feel free to ask any questions at any point. If you want to, now that we are going to recap on the processing using memory approaches that we covered yesterday, if you happen to have any questions related to yesterday's lecture, is a good opportunity now to clarify anything. So the first one of these proposals that we covered yesterday is RowClone, a way of performing fast and efficient and energy efficient in-DRAM boot data copy and initialization. Remember that this is based on a very simple and intuitive idea. You can activate one row. This will transfer the row to the local row buffer. If right after that you activate a second row, that will be the destination where the entire row is going to be copied. It's like a read and write operation. Back to back, and that's implemented with two back-to-back activations to two different rows. Okay, we covered yesterday as well the example of compute DRAM, that by changing the DRAM timing parameters, they were able to mimic the back-to-back activation that is needed for RowClone. They did that in real chips, and indeed in most of the chips that they tested, it's possible to do this RowClone operation, even though it's, they are not originally designed for this operation, right? They are off-the-shelf memory chips that were not designed to perform this operation. So it's something really promising, as we discussed. It's possible to do other operations, bulk bitwise operations, such as AND and OR in DRAM. That's what the Ambit paper proposes, and OR and NOT, taking advantage of majority operations. They use majority, in this paper, they use majority operations to implement AND and OR. And they also propose like some extension to or some modification to the DRAM subarray in order to include these rows of dual contact cells that allow us to perform the NOT operation. The basic idea is the triple row activation. We activate 3 rows at the same time, and this basically generates a majority function in each bit line when the sense amplifier is activated. This is another version of the Ambit work, and this is the compute DRAM work that tested both RowClone and Ambit on real chips. Remember that we mentioned as well other memory technologies were similar operations, similar row copy operations, and and bitwise operations are possible. PNA2BO is a very good example of that on emerging non-volatile memories as PCM. And remember as well the SIMDRAM framework that allows us to create complex functions, arbitrary functions that run using DRAM, taking advantage of the majority functions and not operations. Other works that I briefly mentioned yesterday, this one, Pluto, presented this week at Micro, enables massively parallel computation in DRAM using lookup tables. It requires some more modifications of the DRAM subarray, basically because you have to check indices to make sure that you are accessing the right elements in the lookup tables. Keep in mind as well that here you are in every single subarray, we are going to be performing multiple queries at the same time, because in the end, in the subarray, you have many inputs and can have also many outputs, many query results after accessing the lookup tables. So that's why, it has certain complexity, because we need to identify when one particular input matches the particular index that we are accessing at that time. Flash Cosmos is the let's say ambit for NAND flash memory. As you may remember, this is very recent work, just started, but probably something that can still have a long run. There will be many things to consider here. The need for an ISA, the need for providing users with a way of implementing arbitrary functions as well, same as we are able to do using DRAM with the SIMDRAM framework. So there is for sure more to come in this direction. Okay, so that's say summary of what we covered yesterday about processing using memory. Today we talk about processing near memory in the first part of this lecture. We need to think differently from past approaches. We should see or can see memory as an accelerator in order to enable more data-centric systems, and there are different ways of doing it, right? One can be processing using memory, the other one can be processing near memory. The idea of processing near memory has been around for many years as well, but it took, it became, let's say, more trendy in very recent years, like the last 7-10 years, with the arrival of 3D stack memories. As you may remember, these 3D stack memories are composed by multiple layers of memory, typically DRAM, and a logic layer, right? In this logic layer, there are some memory controllers in order to access data in the different layers, right? The access to data is through these vertical connections that are called through silicon bias, through silicon, because they go through the multiple layers of silicon, right? And there is also some extra area in this logic layer that can be used to embed some small processors or some small processing elements. They can be maybe processing general purpose cores, something that allow you to have more general purpose computation, or they might be application specific. We are going to see both examples today. As you see, memory layers and logic layer. And there are other 3D technologies. Not only this one corresponds to HMC, then we also have another standard, the high bandwidth memory, HBM, which indeed has been more successful over time. HBM is widely used by multiple vendors like AMD, Nvidia, Xilinx as well, and for FPGAs indeed the hybrid memory cube was discontinued. That's from the commercial perspective, let's say. From the academic perspective, we can see all of them as very similar, right? Because they stack multiple layers and they provide higher bandwidth and lower latency to elements, potential elements that you may have in the logic layer, and also to the external processors. So one thing as well, before I forget, because it will be important, is that usually these memories are, well, divided into multiple layers, as you see. HNC in particular is divided as well into so-called bolts. Bolts are like, let's say, like the horizontal subdivision of the layers, right? And this area here could be a bolt. It has its own memory controller. Here you have another area and direct access through a memory controller residing here. So that's how the HMC memory is divided. I'm just clarifying this because, as you can imagine, we will be able to have different cores or different accelerators in different bolts, and they may eventually need to communicate in some way, right? And they will have, let's say, local access to whatever is placed, the part of the DRAM layers that is placed on top of them, while they don't have direct access to other bolts, right? To the data residing in other bolts. This is a table about the DRAM landscape around 2015. What we have these days is more or less the same. It's an evolution of this. Indeed, you can already find DDR5 chips in the commodity segment. You can also find GDDR6 for graphics. In 3D stack, HVM has evolved. Now vendors are working or started to incorporate the HVM 3.0 standard to their systems. But yeah, I think that this picture more or less shows very complete overview of the landscape of DRAM-based memories. So when it comes to creating processing in memory systems with these type of memories, and for now we focus on 3D stack memories, but most of the things that we are going to discuss for 3D stack memories are applicable to 2D memories as well, to things like the Ndp architecture, for example, that is 2D memory, right? It's implemented on DDR4 chips. But yeah, let's start with the 3D stack memories because they have very clear advantages. It's something I mentioned yesterday. When you try to create logic inside a DRAM chip, same as AppMem did, it's going to be very challenging to have a powerful core. The reason is that technology itself is for different purposes. DRAM technology is not created to have fast switching transistors, for example, and that limits the design of the processing elements or accelerators in that type of technology. In 3D stack memory, the advantage, at least in principle, is that in the logic layer is CMOS, so there you can have true CMOS logic, right? And that is for a general purpose core or for an accelerator. So let's start with different potential approaches to PIM using 3D stack PIM. First question is, what would be the performance and energy benefits of using 3D stack memory as a coarse-grained accelerator? When we talk about a coarse-grained accelerator, what we mean is that we are offloading entire operations, entire functions, not just, or entire kernels, not just individual operations, such as you can do to atomic unit near the L2. Remember that I mentioned that example recently. There are different ways of doing this as well. One way is changing the entire system, creating a complete external accelerator, as it could be a GPU or an FPGA, but now created using 3D stack memory. The second possibility could be to perform some simple function of loading. You keep using the CPU most of the time, but from time to time, some functions, some small kernels or simple kernels are offloaded to the PIM side. We are going to see a couple of examples of these. And the other question that we will answer in this part of the lecture is what is the minimal processing in memory support that we can provide. If we don't want to change the entire system, or we don't want to design a coarse-grained accelerator because we don't need it, what could be minimal processing in memory support? And that will have the advantage, it will come with minimal changes to system and programming. And we are going to see at least one example of these today. But let's start first with the idea of using 3-stack memory as a coarse-grained accelerator, and then we will go to the other ones. The first one proposes to change the entire system, or in other words, proposes a completely new accelerator for a special type of workloads, same as you can have off-chip accelerators, external accelerators such as GPUs or FPGAs. We could also fabricate an accelerator based on 3-stack memory. And one good example of where this could be really useful is graph processing. Graph processing is it's not really so complex, but it has certain complexities when it comes to running these workloads on real systems and with good performance, with good energy efficiency. And one reason for that is that graphs are large and they become larger and larger. Here you have on the slide some numbers for real world graphs corresponding to Wikipedia, Facebook, Twitter, or Instagram. I'm pretty sure if you compare these numbers in terms of number of users or pages, you compare them to numbers in the year 2022, probably, they will be much more, right? So this information is represented in terms of graphs because those graphs are important for certain analysis that these companies do. In order to know their users, for example, how they are connected, for example, and this data is growing more and more over time, right? And when it comes to processing these large-scale graphs, we have serious scaling issues, performance scaling issues. And here you can see for motivation, here you can see how the performance of some graph processing algorithms compares when using 32 cores or when using 128 cores in a system. Observe that the performance improvement, the speed up, is only 42%, while we are using 4 times more cores, right? And what's the key reason for that? The key reason is that these cores, either if you're using 32 or you're using 128, are most of the time accessing memory because they need to go through edges and vertices of these very large graphs, right? And in the end, in this type of algorithms, there is not so much computation. So arithmetic intensity is low, right? And that's what makes that the memory bandwidth gets saturated, the access to memory is overwhelmed, and we don't see a linear scaling in speed up or in performance when scaling the number of cores. And I have already mentioned the key bottlenecks for graph processing, but here you can see a very good example. This is Pagerank. It's a graph processing algorithm is widely used in many in some real world applications. As you see in this Pagerank, what we are doing is going through with the outer loop. As you see, we go through all the vertices of the graph, and then we go through the successors of these vertices, the neighbors of these vertices. And for these neighbors, W, we update certain characteristic, that is the rank, the next rank. The way that we update that is by simply accumulating the result of a one multiplication. We take the current rank of the vertex V, let's say the parent vertex, multiply by a weight and accumulate to update the next rank of the successor W, right? As you see, there is not much computation there, and it's only 2 operations, right? 1 multiplication and 1 addition. But also, depending on where the neighbor resides, we may have very regular accesses to memory, right? So first thing to do is to access V And V has certain neighbors. We have the addresses of these neighbors here, but these neighbors might be scattered over the whole memory, over the whole data structure that contains it. So sometimes we'll have to access here, sometimes here, sometimes here, and then we perform this simple multiplication and one accumulation, right? So as you see, there are frequent random memory accesses. They are random because if you think about the graphs, their structure is more or less random as well. Think about a graph representing Facebook users. You have some friends, you have some contacts in Facebook, right? And they may be the same of another person living with you in the same apartment, let's say, but you may also have completely different connections in this social media, right? That might be scattered all over the world. And that makes that also how these or where these neighbors are in the graph might be in very far away memory locations, right? So that's why we have frequent random memory accesses when visiting the neighbors. Also, there is little amount of computation, as you see. So in these particular cases where memory access is overwhelmed and arithmetic intensity is low, processing in memory makes a lot of sense. What the Tesseract paper, the Tesseract system proposes is a coarse-grained accelerator for these type of workloads. And here you can see how it's first connected to the host processor. This could be connected through PCI Express bus, for example, similar to other external accelerators. And then this is the whole accelerator itself. In this case, you can see that there are 4 by 4 of these squares. Each of these squares represents a cube of HMC memory or 3D stack memory. And as you know already, the 3D stack memory is composed by memory layers and logic. What do we have in the logic layer? We are going to have multiple small cores, one corresponding to each of the bolts of this 3D stack memory, and near the DRAM controller that accesses the layers on top of it. And then there is some crossbar network, right, for communication across the cores. So remember that I mentioned all of that earlier. If you look at the internals of each of these cores, you'll see that it's pretty simple. It's just a small in-order core, not a surprise, right? If we put here a much more powerful core, it will also generate much more heat, and that might rise the temperature over the levels that are tolerable by the 3D stack memory. So we have this in-order core that is pretty simple, and then there are a couple of more, a few more components. Basically, this message queue is for communication with other cores, and then we have these two units. It's a line prefetcher and a message trigger prefetcher that are used to bring data early in advance before it's going to be needed by the core, right? And as you see, well, both the buffer, the PF buffer and the in-order core connected to the DRAM controller to access the layers on top, and then this network interface to communicate with other cores through the crossbar network. So this message queue allows these in-order cores, these different cores, to communicate via remote function calls. And they are used for very good purposes. They are used to offload some computation from one core to another core, whenever one core needs to access data that resides in another vault. That's going to be very efficient for this type of workloads and in this kind of system in particular. So communications in Tesseract, how do they happen? It might happen something like this, right? The graph is, if we see the whole picture of the accelerator, you see that the graph itself, vertices and edges, they are mapped onto the memory of the whole accelerator. That's why here in the figure, we see like multiple nodes and edges and how they are connected, right? If you are lucky, the neighbors of this node will be in the same stack, maybe even in the same vault, but that's not going to be the normal thing. The normal thing is that you'll have, in order to update a neighbor, you'll have to go to another memory stack, and then inside the memory stack to one specific vault, right? So in order to do these operations efficiently, the core that is updating the neighbors for a particular vertex V can have the ability to communicate via remote function calls to other cores and offload computation to them. And that's what we indeed see in this figure here. In vault 1, for example, let's assume for now that they are in the same stack or in the same queue. But in vault 1, we have one core. This core needs to update the neighbors of vertex V. Here we have the whole list of neighbors, these addresses of neighbors W, and but the neighbors are in different places. For example, that W neighbor that is there is in vault 1. So what should we do? We can use this non-blocking remote function call in order to perform the update operation. Remember that the update operation is what we have exactly there, in order to perform the update operation in the core that is in charge of the other vault. So that's basically the idea of this communication pattern that is needed for these particular workloads, right? Because they are non-blocking, what that means is that after issuing this put operation, this remote function call, the core in vault 1 can continue the execution. It's non-blocking, right? So it can continue and go to the next successor, and at some point go to the next vertex that was assigned to this core, okay? At some point, you need to make sure that all the updates were done, right? Before performing the next iteration of the algorithm. And in those cases, you will use this barrier, because you want to make sure that all communication happen. But in the meantime, there is not so much rush. Let's say that the execution of these remote function calls can be done asynchronously. Okay. So how does this work? Send the function address and arguments to the remote core, store the incoming message to the message queue. Remember that we have the network interface to access, to communicate with the external cores. We receive function, address of the neighbor, and also the value that needs to be added to the rank of this neighbor. We place them in the message queue, and at some point, the remote core will go to the message queue and will execute it. When this operation, when does this happen? Either when the queue is full, of course, because the MQ has a certain size, limited size. So either when the queue is full or when cores reach to a synchronization barrier, right? Is when the specific functions that we have there are executed. Okay, and then it's possible to do prefetching for some operations. The core will really need to bring data from other vaults or from other parts of the memory. So you can either do line prefetching that basically prefetches the next cache line and this is especially useful when you have streaming access patterns. In other cases, prefetching is done based on the data, based on the information that arrived at the message queue, right? So this message trigger prefetcher has also the ability to check the messages here, see what addresses will be needed for later computation, and request data from other vaults that might be needed. So as you see, Tesseract combines both these remote function calls. Somehow you send the computation somewhere else to happen. In other cases, it might be more beneficial to do prefetching, bringing data and operating in the same vault. So that's more or less the idea. I don't know if you guys have any questions at the moment. We can continue. Tesseract was evaluated to several baselines. The first of them is at the 32 out-of-order processors that you can see on the left-hand side, and DDR3 memory, a total bandwidth of 102 gigabytes per second. The second configuration is exactly the same, but replacing DDR memory with HMC memory that is higher bandwidth, providing 640 gigabytes per second. The third baseline is also using HMC memory, but in this case, instead of using out-of-order cores, here we are using in-order cores, a total of 512 in-order cores. This is like a many-core processor. And finally, Tesseract, that is the coarse-grained accelerator with up to 32 Tesseract cores in each of the bolts, as you see. So here we have not the bolts, in each of the cubes or stacks, right? Here we have 16 stacks or 16 cubes, 4 by 4, and each of them has 32 cores. In total, the internal bandwidth that these Tesseract cores can receive is 8 terabytes per second. So there you can see where is the inherent advantage of a processing in memory accelerator. Is that internal bandwidth is much higher than the external bandwidth that can be enjoyed by the external processors. And here you can see some performance results. This is a speed up over this one. So results are normalized to this one. When you increase the bandwidth from DDR3 to HMC, there is clearly some performance improvement. It's not amazing. Remember that the bandwidth of HMC is like 6 times larger than the bandwidth of DDR3. Despite that, the performance improvement is not that high for these baseline configurations. But as soon as we start using Tesseract with much higher bandwidth, the speed up that is achieved is something between 9.0 and 13.8, depending on whether we are using prefetchers as well or not. And these are also some, it's a related plot, this one corresponding to memory bandwidth consumption. So how much of the provided bandwidth is exploited when you use DDR3 memory or HMC memory or Tesseract, right? So it's still the 2.9 terabytes per second that are obtained with the Tesseract system are far from the 8 terabytes per second that is the peak bandwidth of the Tesseract system. So what that means is that even more memory-bound workloads with even lower arithmetic intensity could still get benefit of that extra bandwidth that the system provides. And another interesting analysis here is what really improved the performance. Is just the increased memory bandwidth. Okay, it's clear that the increased memory bandwidth provides some extra performance, but it's also the design of the system and the way that this system is programmed. And indeed, we see something interesting here. If you evaluate, because in the end this is simulation, right? You can shape the system and configure the system the way you want in simulation. So if you compare the performance of the baseline HMC with, the multi-core HMC configuration with these 512 in-order cores, remember, and artificially increase the bandwidth to something that is the same bandwidth as Tesseract, you will see significant performance improvement, 2.3 times, but it's still not that much compared to the extra amount of bandwidth that we are providing. However, if you change the way the system is designed, you can even exploit that bandwidth much better. And in some sense, we are creating an accelerator that is specialized for these workloads, right? And from that tailored design of the accelerator and the programming model, we can achieve significantly higher speed up, right? So I think this one is interesting because we see that it's both increasing the bandwidth, but not only increasing the bandwidth, but also modifying the system itself, the way it's built the system, the way this system is programmed. In terms of energy, we also see very good improvements, up to eight times energy reduction over the HMC baseline with out-of-order cores, with external out-of-order cores. And yeah, in order to summarize some advantages and disadvantages, one advantage is that Tesseract is a specialized graph processing accelerator used in processing in memory, large system performance and energy benefits, as we have seen, and takes advantage of 3D stacking for an important workload. And it could potentially be more general than just graph processing. In the end, Tesseract is composed by in-order cores. These in-order cores can have relatively large instruction sets, so they can be relatively general purpose. So you could map also other applications onto this accelerator as well. Disadvantages: it changes a lot the system. Now it's a completely new accelerator. It requires a new programming model, requires the specialized cores for graph processing, and it's not something like this wouldn't be cheap, right? 3D stack memories are more expensive than 2D memories, and that's where most of the cost would be coming from. It still scalability might be limited by off-chip links or graph partitioning. I didn't point out to that potential problem when talking about the system itself, but in the end, we have different cubes. These different cubes are connected in some way, right? There is a network, a 2D mesh, as you may have seen, and these links, these connections provide some bandwidth, but not as much bandwidth as the internal bandwidth of the cubes. So in the end, we have a bottleneck there, right? And if the graph is very regular and one particular core needs to, send requests, send these remote function calls to many other cores in the accelerator, the bandwidth, the smaller bandwidth of the off-chip links will end up limiting the scalability, right? Some techniques that have improved this Tesseract work afterwards are around the idea of a smart partitioning of a graph, maybe even doing some pre-processing to understand the graph, to analyze how the different nodes, different vertices in the graph are connected, and then map them onto the hardware in a more efficient manner. Okay, and this is the paper. Now, yeah, let's go with another example. This is also, we can also consider a coarse grain accelerator because we are going to offload entire functions, but it won't be, let's say, the whole program running on the accelerator. It's more like part of the computation is done on the CPU, part of the computation is done in memory. This part of the computation is a simple function. And a good example of this is the Google Workloads paper. We have already mentioned this paper in previous lectures because it has some interesting motivation numbers, right? Like 62% of the total system energy is consumed on data movement. You might remember that number. And energy consumption is very important in these consumer devices. Yes. How does it look, the entire data movement? Yeah, it's a good point. I don't have that information here. And probably it's not even, that analysis is not even in the Tesseract paper. But I can point you to at least a couple of papers that build upon Tesseract. They analyze the data movement across different cubes. Probably they also have energy measurements and propose different ways of partitioning graphs that are more efficient. But yeah, I don't have the numbers here, but I can later point to specific papers that have worked with that. Okay, thank you for the question. Yeah, I was saying that energy consumption is important for consumer devices. These devices typically, like an iPad or cell phone or smartwatch, they typically rely on batteries, and we want to, extend as much as possible the lifetime of the battery. In this work, 4 important workloads are analyzed: Google Chrome, TensorFlow Mobile and the video playback and video capture of BP9 that is used in YouTube, for example. And yeah, for motivation, you already know this, a lot of energy cost on data movement, 62.7% of the total system energy is spent on data movement. So a potential solution is to move computation closer to data, place some compute unit near the DRAM, as you see there on the right-hand side of the figure. There is a challenge, the limited area and energy budget. In this particular work, we are also considering 3D stack memory. As you know, 3D stack memory, you have a logic layer where you can place some compute unit, but you first don't have a whole lot of area. It's just the extra area that is in the logic layer, and also you cannot spend too much energy, because spending too much energy will rise the temperature of the system, and that can affect the reliability of the system, right? Okay, so let's use PIN to reduce data movement for these particular applications. The second key observation is that data movement for these applications comes from the execution of simple functions, and one can design lightweight logic to implement these simple functions in memory. This lightweight logic might be a small embedded low-power cores that are more general purpose, or they could be small fixed function accelerators, an accelerator that is optimized or is designed for BP9 codec, for example, not for something else, right? And in this work, we have the analysis of both. Offloading to PIM reduces energy and improves performance, and we will see more detailed results next. As I said, these are the workloads that are considered in this work. The first one that we talk about is TensorFlow Mobile. TensorFlow Mobile is used in these consumer devices for neural network inference. As you see, you input some image, for example, and obtain a certain prediction. It was measured in this work that 57.3% of the inference energy is spent on data movement, and 54% of the data movement energy comes from two operations: packing and unpacking and quantization. They are pretty simple operations, but they require a lot of data movement. Why is that? Because in packing, what we are doing is taking a whole matrix and packing them, preparing it to, reordering the elements, somehow changing the way these elements are stored in memory in order to later minimize cache misses during matrix multiplication. So it's a pre-processing step before the matrix multiplication that is typically executed in layers of a neural network, as you already know. So we reorder the elements in order to later do more efficient tiling, right? That's what packing is about. But this packing operation is reading one entire matrix and then writing it back, and only just to change where some elements are located or where elements are located. So essentially, there is no computation or very little computation. It's mostly about data movement. So that's why up to 40% of the inference energy and 31% of the inference execution time is spent on packing. And the data movement in packing accounts for up to 35.3% of the inference energy. So, and as I said, it's simple data reorganization process that requires simple arithmetic. In the case of quantization, what we do is converting 32-bit floating point numbers into 8-bit integers. That quantization is pretty widely used in neural networks these days, in particular for inference, for sure. Because this, in the end, is going to improve the inference execution time and the energy consumption. But it's also costly in terms of data movement. Why is that? Because you need to go over all the elements, all the inputs that you want to do inference for, and that's basically reading the entire input, performing some simple operations, in this case, shift, addition, and multiplication, and then write back. So again, a lot of data movement. So we can compare here how the energy improved by tackling, well, in particular, we were talking about Tensorflow Mobile, packing and quantization. You see here the results. There is a significant energy reduction over the baseline for both the configuration with pin cores and the configuration with accelerators. And there you see the actual numbers, 49.1 and 55.4. One minor observation, but also interesting one. Remember that packing has even less computation than quantization, right? So it's even more about moving data rather than computing something. That's what explains that the improvement from pin cores to the specialized PIM accelerator is smaller here than here, right? Because the accelerator itself is accelerating the computation. That doesn't need to change the bandwidth, right? So that's a minor, but I think interesting observation here. If we check the runtime, there on the right-hand side, we have TensorFlow after proposing PIM solutions for both quantization and packing and unpacking, and these are here at the bottom. You see the performance improvements or the speed ups for the whole TensorFlow. Okay, second workload to consider today is Chrome, the Google's web browser. So here you just see some explanation of how Chrome renders a web page. First of all, we have loading and parsing. The page comes from the network, and we first need to do some parsing. Then we have the layouting, where these two steps calculate the visual elements and position of each object, and then the painting stage, where we first have the rasterization that generates the bitmaps, essentially the images that will be sent to the GPU for compositing and showing them into the final screen image. In the analysis of the Chrome browser, we consider that first part, that is the loading of the web page, but also two other functions that are important for a satisfying user experience. One is the smooth scrolling of web pages, and the other one is quick switching between browser tabs. It's quite normal that in the browser we have multiple tabs that are open, and we may want to switch at some point from one tab to another tab, and maybe then a third tab, and so on, right? If you think about the tabs themselves are different processes, are independent processes. If you are not using a tab, it makes no sense to have that data, let's say, active. So what the browser typically does is compressing those pages. That's something we are going to see next. So we are going to focus on these two, page scrolling and tab switching, but both include page loading, right? Because both, if you are scrolling over a page or you are switching tabs, you'll have to pay to load the page. So let's start first with tab switching. In tab switching, as I mentioned, each tab is a separate process. So the main operations during tab switching is, first of all, switch the context, second, load a new page. And these, it's very active or very expensive in terms of memory consumption, because pages reside in DRAM. But if the pages are not used, it makes no sense to keep them active, keep them uncompressed. So what Chrome does is that it compresses them in order to reduce the memory footprint of each tab and places them in some part of the DRAM that is called ZRAM. At some point, whenever the user wants to access the compressed tab, the CPU will simply go to the ZRAM, perform the decompression, and show the page. Was done some data movement study in this paper to analyze what was the cost of data movement for the tab switching operation. The authors emulated a user switching through 50 different tabs, and they made two interesting observations. The first one is that compression and decompression contribute to 18.1% of the total system energy. And in total, when switching through these 50 tabs, there is a large data movement between CPU and ZRAM that is like almost 20 gigabytes for 50 tabs. So there's a lot of data movement there, as you can see. So what's the key idea when using PIM accelerator or a PIM core here? Instead of in the baseline, in the typical CPU-only system, where you want to swap out pages, then you need to read the compressed pages from memory to the processor, read the pages, compress them, and then write them back onto the ZRAM. With PIM, what you can do is simply offloading all the compression to the memory side, to some PIM core there, or some PIM accelerator, and directly write to ZRAM. In between, in the meantime, the CPU can simply be idle or can perform other tasks. And that can be done by, at the same time, saving a lot of cheap data movement. So that's the basic idea. Yeah, so large amount of data movement happens during tab switching due to compression and decompression, and both functions can be implemented in PIM. So can benefit from PIM execution and implemented as PIM logic. And yeah, that's, let's say that the main takeaway of this work, 62.7% of the total system energy is spent on data movement for these workloads. Here you have seen just a couple of them. You have many more details in the paper. This idea of offloading certain functions or certain operations that does not only apply to CPUs, it can also apply to GPUs. And yeah, we could potentially see, this is the main GPU, these are the 3-stack memories around the, or different cubes of 3-stack memory around the main GPU. And here inside the logic layer, we could have a small GPU cores. They are called SM because SM means streaming multiprocessor. That is the name that NVIDIA gives to the GPU cores. But as you see, there is in the logic layer, we have a number of SMs, small SMs, probably not so capable as the ones that we have here, but they can be good for certain operations. And that's something that was, by the way, this actual configuration is not different from, not much different from the configuration of current GPUs. If you look at current GPUs with HBM memory, you will see the main GPU in the middle, and then there are 5-6 stacks of HBM memory. The only thing that is not there yet is a small SMs inside the logic layer or somehow somewhere in the memory stacks. So this idea of using processing in memory for GPUs as well has been explored in multiple works. This is one of them, a pretty interesting one, transparent offloading and mapping that proposes a way of identifying sections of code that might benefit from execution near the memory and performs a programmer transparent offloading and scheduling and offloading for those. And this is a somehow similar work, but targets the offloading at a different granularity. The previous one focuses more on shorter pieces of code, while this one is offloading entire functions to the memory side. We will talk about this one later. It's another example of when to offload certain operations, certain functions onto the 3-stack memory or the PIM cores in the 3-stack memory, in particular for pointer chasing applications. But we will cover this one in more detail later in this lecture. And here you have also a couple of examples of processing near the memory controller. In this one, this first one proposes a way of accelerating cache misses, taking advantage of some logic in the memory controller. This one is this kind of run-ahead execution in the memory controller. So in some ways, sort of processing in memory techniques as well, with the particular characteristic that the logic is not in the logic layer of 3-stack memory, is near the memory controller. And I think I mentioned this one yesterday or in a previous lecture, is another type of near data processing, in this case using an Fpga that is connected through a silicon interposer to HBM memory. And this is another example that also considers similar configuration, but not for an Fpga, for a specialized accelerator. GenAsem is a specialized accelerator for approximate string matching that can be used for genome sequence analysis. And this accelerator is connected to HBM memory through silicon interposer as well, in order to obtain higher performance, of course. Yeah, I will probably talk in more detail about this work in one later lecture, where we cover works related to bioinformatics applications. This one is another one, also interesting one, that also follows near data processing approach. That's this NATSA accelerator is for time series analysis. I don't know if you're familiar with time series. In reality, time series is just a sequence of values that arrive over time. This work can apply to many different domains in the real world, from electrocardiograms to earthquake analysis or vigilance or many other applications where you have a long sequence of data and want to find specific patterns in this long sequence of data. Just for example, if you want to identify some heart issue, you need to analyze the entire sequence in the electrocardiogram and try to find a specific representative sequence that tells you that there is some issue with the heart of the particular person, right? So it's just one example. These, as you can imagine, are also handling a lot of data. So there is little computation because it's mostly comparing, right? And that's why these applications can also benefit from near data acceleration. Next use case of 3-stack PIM or 3-stack memories to create processing in memory systems is a system that provides minimal processing in memory support. And this has the advantage that requires minimal changes to system and programming. That's something that was tackled here in this PIM-enabled instructions paper that we are going to cover now. The goal is to develop mechanisms to get the most out of near data processing with minimal data costs, minimal changes to the system, and no changes to the programming model. The key idea is to expose each PIM operation as a cache coherent, virtually addressed host processor instruction that is called PI, that operates only on a single cache block. That's important, right? Because if it operates on multiple cache blocks, it might turn out that the different cache blocks are in different vaults, for example, and that makes things much more complicated. But if you're operating on a single cache line, it will be in the same place. All bytes there will be in the same place. The PIM enable instructions or the PI instructions look more or less like this. One PIM add is an addition operation that is going to be performed on the memory side. This requires no changes to the sequential execution programming model. It's just replacing the conventional add with this PIM add. No changes to the virtual memory, minimal changes to cache coherence, and no need for data mapping because each PI is restricted to a single memory module because it targets a single cache line. The second idea is to use dynamic scheduling. Decide where to execute a PI depending on where the data is located, because your algorithm might have been, your program might have been processing some data that you need to update later using an addition, for example. But if this data is already in the cache, makes no sense to offload to the memory side, right? So that's why here we try to compute where it makes sense, where the data resides. The motivation for PEI is again the Pagerank algorithm. You already know it. We go through the vertices of a graph, we update the successors, and in the end, updating the successors is just adding certain value. The value is weight times rank of the parent vertex. We add this value to the next rank of the successor of the child vertex. If you do this in a conventional architecture, just for that operation, you need to read the rank, read that element, next rank, bring it to the host processor. And even if that's only 4 bytes or 8 bytes, you're reading an entire cache line, typically 64 bytes. And then you update it and write it back. So this means 64 bytes in, 64 bytes out, 128 bytes that are moved, maybe just for one addition. If you do the operation in memory, if you have an in-memory addition, such as this PIM add, you simply need to calculate the value first in the host processor and then execute the PIM add operation. Send the value to the main memory. And that's only 8 bytes in and 0 bytes out of memory, right? So it can be, I mean, it's very promising. This idea is very promising. However, current CPUs, current GPUs are already quite well optimized to somehow try to alleviate data movement bottleneck. They have large caches. And for example, if you have very small graphs or very small data sets, it might turn out that these data sets fit most of them, if not entirely, in the cache hierarchy of the CPU. In those cases, it doesn't make sense to send computation to memory because in the end, you are in the beginning of the program loading an entire graph, and this graph, if it's small enough, is going to fit in the cache, in the L3 cache of the CPU. Only when the graph starts being significantly larger, you have many more vertices and you have many more edges as well, you will see some performance improvement, some speed up. So in memory computation for those large graphs, however, for small graphs, caching is very effective. And these, I mean, these should make us think that executing always in memory is not always a great solution. It's much smarter if you offload based on the the particular workload and the particular graph in this case, whether it resides in the cache or not. Okay, yeah, we are going to, well, see some of the, in principle, you can support any operation, right, and on the memory side. In this work, they propose the idea and then they propose as well implementing in memory accelerators or small processing units for certain operations that are necessary for some, I mean, for the applications that they consider. But, you know, you could propose different PIM operations as well. They will be executed either in memory on the processor based on a dynamic decision. So it's important to have some way of monitoring locality that is low cost. Also, it's important to be cache coherent, virtual address, single cache block only. This is something that we already mentioned. Atomic, the operation, these PIM add are going to be atomic operations between different PIs, but they are not atomic with normal instructions. When we talk about normal instructions, we mean, for example, that calculation at the top, right? That multiplication at the top. For those, you don't really need to keep consistency in the ordering, and that's why eventually you may need to use a barrier that in this work is called p-fence. Okay, so it's practical to do this single cache block restriction because this way you don't need to, you know, just need to worry about one cache block and don't need to go to other units to execute the operation or something. So this has benefits in terms of localization, interoperability, and simplified locality monitoring because you just need to monitor where one particular cache line resides. And yeah, we are going to see some initial evaluations for these 10 emerging data-intensive workloads. Some of them are graph processing, data analytics, also machine learning and data mining. And here you have a summary of results, performance improvement and energy reduction. Yeah, you have here the whole list of the workloads that were considered. First ones are graph processing. Here we have also data analytics, such as hash join, or even machine learning, like string cluster or SVM. And the work uses 3 different input data sets in order to study what's the impact of data locality. When you use the smaller data set, then probably the CPU will perform better in comparison to the pin system. So here in this plot, we have performance delta for large data sets. This is for PIM only, and for the locality-aware mechanism, you offload only when the data is not in the cache. We will see later a little bit more detail about this locality-aware monitor. But yeah, you can see that, well, there is some interesting performance improvement in all cases. It's usually slightly higher for the locality-aware execution. And yeah, this is the normalized amount of off-chip traffic, off-chip transfer. So as expected, in most of the cases, we see a significant reduction of the total data movement. However, if you do it you obtain the speed up for small data sets, what's going to happen is something like this, right? Because these data sets are small, they likely fit in the cache hierarchy of the host of the CPU. So that's why if you go for a PIM-only execution, makes no sense, right? Makes no sense to offload for these small data sets. If you have the locality-aware implementation, probably the locality monitor will select execution on the host most of the time, and that's why we see that the performance is more or less zero performance improvement. There is also only one exception. I think that one is histogram calculation. Probably in the histogram calculation, the PEI instruction is used only at the very end, so just the histogram remains in memory, and that's why even if the data set is small, there is no let's say drawback of doing the computation in memory, but that's just an exception. And these are results for off-chip transfer, and these are for medium data sets. So with medium data sets, we start seeing that even the PIM-only execution can obtain some performance improvement with respect to the host. Now the data set doesn't fit entirely in the cache hierarchy, and this is why processing in memory makes more sense. And for sure, for large data sets, as we have seen earlier, is the best choice. And in terms of energy consumption, here you can see also some energy results for small, medium, and large data sets, as expected, higher energy reductions for large data sets. So advantages and disadvantages. Advantages is simple, low-cost approach to processing in memory. There are no changes to the programming model or virtual memory, and dynamically decides where to execute an instruction. Disadvantages: doesn't take full advantage of processing in memory. Single cache block restriction is limiting. It's limiting the complexity of the operations that you can offload in this way. Right, so this approach makes sense when the operation to perform is relatively simple, such as an addition or small calculations that just require to access a single cache block, right? And that's good in some sense, but also has its own disadvantages. And this is the paper. We have already mentioned this one, transparent offloading, also these two. And granularity, offloading granularity at different granularities has been explored also in other works like lazy ping and Conda, but we are going to mention them later in the second part of the lecture, where we cover how to enable processing in memory. So As you see, processing near memory is another way of doing processing in memory that can provide fundamentally energy-efficient data-centric computing architectures, high-performance data-centric computing architectures, and computing architectures with minimal data movement. Okay, so let me know if you guys have any questions. No questions? Okay. Yeah, I propose a 10-minute break, and we continue with the second part, how to enable adoption. Okay. Okay, I think it's a good time to continue. Yeah, we are done with the two main directions in processing in memory, processing using memory, processing near memory. What we are going to discuss in the rest of the lecture are different directions that is still necessary to pursue in order to enable the adoption of processing in memory in real world systems, right? So this is about how to enable the adoption of processing in memory, and there are certainly some barriers for adoption of processing in memory. Starting from applications and software, we need to know what applications can benefit from processing in memory, and we need to develop the corresponding software for processing in memory systems. Programming these processing in memory systems might not be trivial, so that's why we have to put effort on making programming easier, both programming interfaces, but also compiler or even hardware support to programming. We need to deal with other system support and security support considerations, such as coherence, synchronization, virtual memory, isolation, communication interfaces, etc. So we don't want computing systems to become more vulnerable because now they have some additional capability that is processing in memory. We don't want them to be less secure. Runtime and compilation systems for adaptive scheduling, data mapping, access sharing, and control. Yeah, we have already talked about adaptive scheduling, and we are going to review some examples next. And finally, infrastructures so that we can use to assess benefits and feasibility. And this includes, for example, simulators, right? So there were no processing in memory simulators a few years back. After some people have done research in academia, there are now some open source simulators that can be used for further studies. So all these barriers can be solved with a change of mindset. And as you remember, this change of mindset requires to revisit the entire stack from the algorithm to the devices and go there step by step. The analysis of all these barriers for adoption of processing in memory is you can find at least our own analysis in the modern primer on processing in memory. It's section 8, and we are going to talk today about many of these points. You can also find other good reviews about processing in memory in this shorter paper published on the microprocessors and microsystems, or this other one published in the IBM Journal of Research and Development. So let's start talking about the barriers, and let's start talking about potential solutions on how to solve them. The first of these barriers to consider is the PIM runtime scheduling and data mapping. How do we have to map data in a processing in memory system, and when is the right time to schedule computation? And what's the computation that we need to schedule when we have a memory-centric computing system, a system with a host processor, but also processing in memory capabilities? And one good example is the Pei Micro Architecture. We just talked about Pei before the break. Remember that what Pei does is extending the system with some processing elements near DRAM in the logic layer of a 3D stacked memory. These processing elements execute simple operations that we call PIM-enabled instructions, right? Remember as well that in all results, we have seen results for PIM-only execution when the particular operation that is executed here is always offloaded to the memory, and we have seen a locality-aware execution, right? If you always offload to memory, you always offload the operation to the PCUs, it might turn out that the cache line that we want to update with the PEI here, this cache line is in the cache hierarchy of the CPU, because this last level cache is pretty large, and if the data set is not that large, it's not that big, it's likely that the data will be here in the last level cache. So if you insist and offload to the memory side, the first thing you'll have to do is to flash the cache in order for that cache line to get back to the memory, right? And if you do that, well, you are not going to be so efficient, right? Because you need some amount of latency until the cache line is evicted and gets back to is written back to the memory, right? So that's why it's important to have this locality monitor that checks using this PIM directory, checks whether a cache line is in the cache hierarchy of the CPU or not. If it's not, then it executes the computation in the PCUs, in the 3-stack memory. If it's in the cache hierarchy, the cache line is in the cache hierarchy, then it runs in this PCU near the out-of-order core. And this were also some results is a performance improvement for the large inputs. Yeah, we indeed have already seen this plot. It's only that the colors change. But yeah, you can clearly see here that there is some benefit from using the locality-aware scheduling. So this serves as an example of efficient scheduling and offloading that is necessary in processing in memory systems. So this is our first example. The second example we have also discussed as well. We have mentioned this Tom paper where the stacks of 3D stacked memory are extended with some small processors, small SMs in the logic layer. Where should an operation be executed depends on the specific needs of the code that runs on the GPU. And there will be some operations that are better to execute in the near the memory. Some other operations will be better to execute in the main GPU. And the Tom paper provides an automatic mechanism to detect those operations. And similarly, and related to that as well, is how should data be mapped to the different 3D stack memory stacks. Data mapping is especially important in processing in memory systems because in some way we can see them as a distributed system, right? Because we have local memories for the cores that reside in the logic layer or reside near the memory banks, while other layers are far away from these cores, right? So when it comes to mapping the data and deciding where each of the different data structures are allocated in memory in these different stacks, it's better that we do an intelligent decision. Of course, this is challenging. It's not always going to be easy, but it's something to think about as the programmers, for the programmers and the users. Coming up with automatic ways, heuristics, for example, or machine learning-based techniques to decide on the data placement is something that is certainly possible and represents also a very interesting line of research. Okay, any questions here? Okay, this is the Tom paper. Remember, this is also a GPU paper, also how to schedule code. This one is at a larger granularity. As you may know, if you're familiar with GPU programming, GPUs run functions that are called kernels. And typically in a GPU program, you will have multiple kernel calls to probably different kernels with different functionality. Same as we use functions in CPUs and in C programming, for example. So in this work, they do an independent analysis of all the different kernels and decide when it's good to offload one kernel to the PIM side or not. So it's very similar idea. Actually, both works were contemporary. It's mostly that they work at a different granularity. This works at the granularity of their entire kernel, while Tom works at the granularity of a few instructions inside a kernel. Okay, yeah, also, you know, taking care about how to schedule these work, accelerate independent cache misses with an enhanced memory controller, or the other one, continuous run ahead, that also does processing near the memory controller. So these are, you know, one of the things that need to be we have to deal with in order to enable efficient data-centric systems that take advantage, that leverage processing in memory capabilities properly. But if you offload computation to PIM cores, one other thing that you have to take into account is that some of the data may reside in the cache hierarchy, right? We have seen the example of PEI. There we have a simple locality monitor. It's pretty simple because we just need to worry about one single cache line. If the cache line is in the cache hierarchy, we execute the operation in the host. If it's not in the cache hierarchy, then we offload the computation to the processing in memory side. In some cases, the workloads will be more complex. And in those cases, it's necessary to really provide mechanisms to maintain memory coherence between the host and the PIM side. That's especially important when we have concurrent execution of host and PIM, and both host processor and PIM processors are accessing and updating, modifying the same data structures. That was studied in some previous work of our group, and the authors tried to first of all measure what was the impact of using traditional coherence mechanisms that are used, for example, in multiprocessor systems, in multi-core CPUs, such as the MESI protocol, this FG, what is it? This FG here, for example, is implements the MESI protocol between the host side and the memory side, and they compare the performance of the workloads in these systems, in these hybrid CPU PIM systems, compare them to an ideal case where there is no coherence overhead, right? This is done in simulation, so you can also get rid of all the overhead, don't account for the overhead of coherence, and then obtain this measurement. As you can see, it's pretty disappointing, right? By using the traditional coherence methods, we are pretty far from the ideal, that is the yellow bar. In fact, the paper that where this analysis was done is lazy PIM, and with lazy PIM, as you see, we are going to explain it next. But as you see, we are much closer to the ideal. This is the lazy PIM paper, short paper that was first published in 2016, and then the extended version was published in 2019. It's called Conda. So let's talk about Conda. Let's see how to do this, how to obtain or how to manage this coherent support for near data accelerators. As I said, what we are considering here is a CPU and the memory side, where we have PIM cores. Both CPU and memory side are computing, operating on the same data structures, so they may modify the contents of these same data structures. So we need a way of maintaining the coherence between both sides. We are not talking about coherence on the memory side between the PIM cores. We are not talking about coherence on only the host side between host cores. We are talking about coherence across the two sides of the system. We can consider specialized accelerators, and among them, we have near data accelerators. Even though here we call them accelerators in this slide, you can keep thinking about them like, let's say, specialized function units or specialized accelerators, or they could also be general purpose cores. So as you see, the terminology, the terms more or less change from paper to paper, from work to work, but in the end, the idea or what they represent is exactly the same. So this coherence for NDAs, coherence between the NDAs and the CPUs. We have the host processor here. We have the DRAM side, the memory side there with some compute units because there is large communication cost. We use processing in memory, or we use near data accelerators. And as we have seen in the previous motivation, it's impractical to use traditional coherence protocols, for example, such as the MESI protocol. Existing coherence protocols, coherence mechanisms have some problems, is that They partially eliminate some of the benefits of NDA, and then they also, they have a lot of coherence traffic to maintain coherence, and this coherence traffic could be unnecessary. And much of this off-chip traffic can be eliminated if the coherence mechanism has insight into the memory access. The idea of Conda and the idea of lazy PIM is an optimistic approach. In this optimistic approach, there are some challenges related to NDA coherence, but the first thing is to gain insights before any coherence check happens. Second, perform only the necessary coherent requests. Because it's optimistic, what basically Conda proposes is to compute on both sides, expecting that everything will go well, and then check if things really went well or not. Observe that we have on this side the CPU, on that side we have the NDA accelerator, the CPU thread of execution at some point offloads computation, an NDA kernel or a PIM kernel to the memory side. Computation starts there on the memory side, but at the same time, we have concurrent execution from the host, right? We talk about optimistic execution because during all this time, there is no coherence traffic at all. The CPU and the memory side are working independently as if everything was going to go well. And both generate a signature. It's like sort of a summary of the data that has been accessed, like a summary of the cache lines that have been accessed. Indeed, this is implemented with a Bloom filter. And at some point, they exchange the signatures, or the NDA sends the signature to the CPU. The CPU compares with their own signature, and this way they see if they modified the same cache lines or not. If the signatures are completely different, that means that they work on completely different cache lines, they modified completely different cache lines. So then we are good, right? There was no coherence conflict, there was no problem. However, if for some reason they modify data in the same cache lines, they will have to resolve the coherence, and the way of doing that might be to re-execute. Re-executing means that the CPU would move or would write back the cache lines that it modified to the memory side, and then the kernel will be executed again. So as you see, if things go well, it's perfect because there are no coherence requests, no traffic from memory coherence. If things doesn't go well, then, well, you will spend twice the amount of time. But yeah, it turned out that the proposal worked well for the evaluated workloads within 10% and 4.4% performance and energy of an ideal NDA coherence mechanism. And yeah, here you can find the link to the paper. Any question here? Okay. One more is synchronization support. And now we really focus on the PIN side. In the PIN side, we have many cores, each of them near a memory bank, for example, and they may need to communicate, they may need to synchronize. We have already seen some examples of this in the Tesseract system, this coarse-grained accelerator for graph processing. There, we need to have communication between different PIM cores. That's why we have these remote function calls, and we have this message queue, because they need to communicate, right? But that approach is specific to that design, to that coarse-grained accelerator. In a more recent work, we proposed synchron and efficient synchronization support for near data processing architectures, and I'm going to briefly discuss it now. So synchronization is challenging for NDP systems. We are going to see why. One of the reasons is that NDP systems don't have a shared level of cache. The way that threads are synchronized, for example, in CPUs or GPUs, makes use of the levels of the memory hierarchy that are shared, such as L3 in CPUs or L2 in GPUs. But these approaches are not suitable for NDP systems because in NDP systems, we don't have shared level of caches. We may have small caches in each of the PIM cores, and then they have access to the main memory, but they may not even be able to access the same parts of the memory. So we need to think about something else for synchronization and communication of PIM cores. The contribution of this work is Synchron, the first end-to-end synchronization solution for NDP architectures, and you will see some good performance and energy results within 9.5 and 6.2% of an ideal zero overhead synchronization scheme. And synchronization is necessary for many of the workloads that we can potentially execute in PIM systems. For example, graph processing. Here we have the example of single source shortest path, where we are calculating the distance from one node or from vertex of a graph to all vertices of the graph. And if we do a parallel implementation of this algorithm, we may need to update the distance arrays at the same time, or we will have multiple threads of execution, or in the case of a PIM system, multiple PIM cores updating certain arrays. In this case, the distance array, all at the same time, and this may cause conflicts, writing conflicts that we can solve, for example, with atomic operations or with some synchronization primitives like mutexes that here are called lock, right? So here we lock the access to these arrays and the execution of this part of the code, and then after one PIM thread or one PIM core executes this, then releases the lock, right? And that's the way of ensuring right communication and synchronization and making sure that the work, the work is correctly done, right? And this is not only for graph analytics. We can also find, that we need synchronization mechanisms for other data structure, other applications as well. Concurrent data structures, we will mention them at the end of this part of the presentation, because our group has also a work on concurrent data structures for processing in memory. Okay, so what's the baseline NDP architecture that we consider? Is something like this. Remember, this looks more or less similar to the Tesseract accelerator, right? We have multiple NDP units, so they are called in this work. These NDP units are connected to some using some off-chip links, and then inside each of the NDP units we have several NDP cores that have access to the same local memory. This main memory is the main memory for these NDP cores, and they might be a programmable core or might be an accelerator, or they will likely have some small cache or maybe a scratchpad memory, something like a cache, but pretty small. Some challenges in creating synchronization mechanisms for NDP systems. First of all, there is lack of hardware coherent cache coherence support. Remember that we talk about coherence support for in Conda and in lazy PIM, that this was coherence support between host and memory, not between PIM cores. There is expensive communication across NDP units, because sometimes the communication across the NDP units need to go through the off-chip links, and also these systems don't have a shared level of cache. As I mentioned earlier, in some processor-centric systems, synchronization is done through shared level of caches. So that's why all these possible ways of doing synchronization that are based on shared memory are not applicable here. In this context, it makes more sense to have a message passing approach. So the NDP cores are going to send messages to other cores to let them know that they need to synchronize. For example, a barrier, or for example, a lock or mutex. What Synchron provides is hardware support for the synchronization acceleration, direct buffering, of synchronization variables, the hierarchical message passing protocol, and integrated hardware-only overflow management. Because sometimes, I mean, there are some queues, as you will see, and sometimes these queues may overflow, and there is also a mechanism to deal with that. So first of all, hardware synchronization support. We extend each of the NDP units with a synchronization engine. It's a special unit that is going to take care of synchronization. So whenever a PIM core or NDP core needs to synchronize, needs to execute, for example, a lock acquire operation, it will send the request to the local synchronization engine. This avoids complex coherence protocol, excessive atomic operations, and is also low hardware cost because the synchronization engine, as you see here, is pretty simple. It's just a small processing unit, a small table, and some indexing counters. So what we have in the synchronization table is where we keep track of the logs that, in this case, logs that are sent to the synchronization unit and will be sent to other units as well. Yeah, then the communication is hierarchical. If two NDP cores, NDP core 0 and NDP core 1 reside in the same NDP unit, synchronization will stay in the own synchronization engine, right? Because it's only local. But if it affects the rest of NDP units, in that case, we will need to use this hierarchical communication protocol. That's where we first have to define a master synchronization engine so that when the NDP cores generate the synchronization request, they are first sent to the local synchronization engines, and then from there they are sent as in this case, a global lock acquire to the master synchronization engine. And this way, because it's hierarchical, we can minimize the expensive traffic. So Synchron proposes the first end-to-end synchronization solution for NDP architectures. Benefits are high system performance, low hardware cost, programming ease, and general synchronization support. And here you can see some results within 9.5% and 6.2% of the performance and energy of an ideal zero overhead synchronization. Okay, and yeah, and here you have some links to the paper. And actually, if you want to understand more and see, more examples of how to use Synchron or how Synchron is used for different applications, please watch this past lecture from, actually fall 2021. This is another work that I mentioned, concurrent data structures for near memory computing, also an interesting reading. For how to use the concurrent data structures in processing in memory systems. Concurrent data structures are, for example, linked list or skipped list or FIFO buffers, etc. When they are updated by different processing PIM cores at the same time. So how to deal with that? Find a good solution for them. Okay. Any questions until now? Probably many questions, but you will also have to digest all this information, right? Because these are many different works. Well, as you see, I mean, of course, you can go deeper into all of these works if you read the papers, and you will understand much more. And what I'm trying to convey are the key ideas of the different works and how we can try to find solutions for existing problems. So that's the most important takeaway today, is that you get familiar with all these different techniques, or in this part of the lecture, like the challenges of processing in memory and how they can be solved or at least alleviated with different ideas. Memory coherence, synchronization, virtual memory support is also important and necessary for processing in memory systems. There might be different ways of supporting virtual memory translation for processing in memory systems wherever this translation is needed. In some cases, it might not be needed, but as I said, there might be different ways. Probably there is no universal solution for virtual memory support. It will depend on the processing in memory system itself. Now, what I'm going to explain is an example that applies to near processing, so processing in memory accelerator for pointer chasing applications. But if you think about other works, things may change. For example, in the PIM enable instructions work is much simpler, right? Because you the PCUs in that work, the PIM units in that work, they only have to deal with a simple cache line and basically one instruction. What you can do there, what actually the host does is that before offloading the specific operation, the specific instruction to the memory side, it performs the virtual memory translation and obtains the physical address in the host. And then the operation is offloaded. That's an okay solution for that particular work that is relatively simple, right? It only considers a single cache line to be updated by the, or to be accessed by the PIM units. In other processing in memory accelerators, for example, this one, we may need more complex mechanisms to support virtual memory translation. So this work, accelerating pointer chasing applications with processing in memory, that is called Empika for short, you will see the acronym later, has as a goal accelerating processing chasing, pointer chasing inside main memory. Challenges are parallelism and address translation. That's one of the challenges. The reason why this is called Empika is because that means in-memory pointer chasing accelerator. It's based on a couple of key ideas. The first one is to do address and access decoupling, enabling parallelism in the accelerator with low cost. So we are going to have part of the accelerator, one accelerator for address translation, while another accelerator takes care of accessing memory and performing the operation that is needed by the pointer chasing application. And the other idea is to have the Empika page table that is a low-cost page table in the logic layer. So in some sense, we are replicating the page table on the memory side, but in a low-cost way. Key results are something between 1.2 and 1.9 speed up for pointer chasing operations, 16% for the database throughput, and also significant reduction in energy consumption. So as an example of these pointer chasing applications, we have linked data structures that are widely used in many important applications, such as databases, B-trees, key value stores, hash tables, and all these data structures are connected by pointers. And traversing these linked data structures requires chasing pointers. For example, if we have this tree and we want to find A, we want to find the leaf A, we'll have to go to memory, bring H, that is the root, bring the data, check that data. With this way, we find another pointer that is a pointer to E, and then we have to go to memory and bring the data of E, and then we find the address to A, and we can bring A, the data of A, to the CPU. So these accesses are serialized, might be irregular, especially if the trees are very large, and it might take like up to 6 cycles per instruction in real workloads due to the access to data, right? Because it's a very memory-bound operation. So the goal is accelerating pointer chasing inside memory. So we can replace conventional memory with 3-stack memory with some units in the logic layer. The idea is to say, okay, I want to find all the pointer chasing is done in memory, and then we return the data to the CPU, right? That's what this work tries to do. There is a first challenge is taking advantage of parallelism. If you do this computation from the CPU side, you'll have some computation, at some point some memory access, and then you can continue with the execution. If you have an in-memory accelerator, the good thing is that the memory access can be much faster, lower latency, higher bandwidth, and it's faster. As you see, there is some saving in the total execution time. The point is that CPUs can exploit memory level parallelism. You can have, for example, another core that is also running the same workload and can overlap the memory accesses with the memory accesses of the initial core. So in that case, you can be quite good at the CPU and not that good on the memory side if you have a single accelerator, right? So the in-memory accelerator, if you're not careful in the design, will be slower for two operations. So a simple in-memory accelerator can still be slower than multiple cores. The opportunity is a pointer chasing accelerator that doesn't spend long time waiting for memory. So the idea is to decouple the address calculation and the access to memory such that we have two engines, or the accelerator has two parts. In the first engine, address engine, we obtain the address that needs to be read from memory, and then we send that information, that address, to the access engine that takes care of the access. While this is happening, the address engine can compute another address and request another memory access to the access engine, and so on. And this way, we can save time with respect to the execution on the CPU. So address access decoupling enables parallelism in both engines at low cost. So let's take a closer look at the Empika core architecture. As you can see, we have DRAM layers. Remember that this is implemented on 3-stack memory. We have DRAM layers, and then we have the logic layer. In the logic layer, we have memory controller, and then address engine and access engine. Between these two, there is an access queue and a response queue. The access queue is for the address engine to write the addresses that need to be accessed by the access engine. The response queue brings the data to the address engine for further pointer chasing, right? And then there is also this Empika cache, because it makes sense to have a small cache in the near the accelerator in order to avoid some of the accesses to DRAM, and then we have the request queue. So let's, for example, do offload some operations from the CPU. First of all is traversal 1. Second one is traversal 2. Traversal 1 requires the address engine to obtain one address, sends this address to the access engine. The access engine goes to memory and brings data. We can sustain these two accesses at the same time, exploiting, for example, bank level parallelism, and then the access data is sent back to the address engine for, for example, obtaining the next pointer in the tree and continue the access. So that's more or less how it operates. Now, how is the virtual memory address translation challenge overcome? We have a pointer, right, in virtual address space. In the regular CPU, we have TLVs, we have a memory management unit, and they take care of the virtual memory address translation, right? We check the page table, for example, and then that gives us a physical address. That's the physical address in memory that we need to access. But even though this is, conceptually simple, the real implementation in current systems these days uses several levels of page tables, and going through these page tables is pretty costly. It requires these page table walks that in the end are complete loops, going to memory, bringing something, going again to memory, bringing something, and so on. So just for a single memory address translation, you may require up to 4 accesses to the main memory, right? So, and what do we need to do when there is no TLV or MMU in the memory side? And duplicating them is costly and creates a compatibility issue that we don't want to deal with. This is the page table wall, requires multiple memory accesses, as I already said. So what Empika proposes is a so-called Empika page table, completely decouple the page table of Empika from the page table of the CPU. So this is the CPU page table where we map from the virtual address space to the physical address space. These are two different pages. They are located in different places in memory. The Empika page table is going to be a reserved region of the page table of the virtual memory address space, and all the pages that are going to be used by the Empika accelerator are going to be in this region. And this way, this Empika page table that is much smaller than a regular page table, and that actually doesn't have multiple levels as we have seen earlier. It has faster access and low overhead access, right? So it's a page table that is partial to any mapping. It says it's partial to any mapping because it's only a small region of the virtual address space, while the physical address space can be the entire memory, right? And this is how the mechanism works. From the virtual address, we first access those bits of the virtual address are used to access a region table, and then there is a larger Empika table that is the flat page table of a size of up to of 2 megabytes, and then with them we can access a small page table of size 4 kilobytes, and this generates the physical address. So one advantage of this is that the region table is very small, so it's likely going to reside in the cache of the Empika accelerator. The flat page table is larger, but it saves one memory access. We don't need to go repeatedly to memory as you have to do with regular page table workers that you have in CPUs. So this is a way of saving memory accesses and providing this ability of translating virtual addresses into physical addresses. So the evaluation, what we see is, first of all, for some pointer chasing operations such as linked list, hash table, and B-tree, comparing to the baseline, there are some good speed up between 20% and 90%, as you see. These are for databases. The speed up is not so impressive, but it still is good, 16%. And in latency, there are also interesting reductions for query to the database, how long it takes. Well, there is an interesting reduction coming from the use of Empika accelerator. In terms of system energy, there is more or less improvements along the lines of the performance improvements, up to 41% reduction in the energy consumption. And area overhead, well, in this slide, you can see the area overhead in total, it's a pretty low area overhead, and power overhead is just like 1.6%, so 5.6%. Okay, any questions? Okay, accelerating pointer chasing. This is the paper. There are related papers. This one, the virtual block interface, I think I mentioned this one in the first lecture. It's a flexible alternative to the conventional virtual memory framework. It doesn't target, this work doesn't target processing in memory specifically, but many of the ideas that are proposed in this work and are explored in this work could be useful for processing in memory systems as well. In BVI, what is proposed, instead of having a rigid organization of virtual address space for different purposes, you have a much more flexible thing, thanks to the fact that the memory translation is offloaded onto the memory controller. So the memory controller is extended with hardware to perform memory address translation and achieving a lot of efficiency. If you check the paper, you'll see that, or the related talk, you'll see some use cases for heterogeneous memory systems, for virtualized environments, and as I said, this could be potentially a solution for virtual memory for processing in memory systems. Okay, more things. We need infrastructures in order to enable research in processing in memory. And not only that, we also need sample codes. We also need workloads that we know that are suitable for processing in memory because they can be useful for many different purposes, right? They can be useful simply as examples of what processing in memory code or processing in memory application is. And and they can be useful to evaluate improvements, both software and hardware or architecture improvements in processing in memory systems. And we have done a little bit of this work as well. I would like to highlight, first of all, the move methodology and workloads. It's a methodology and benchmark suite for evaluating data movement bottlenecks. In the end, data movement is what motivates us to improve computing systems and make them more data-centric. The move paper proposes a methodology to analyze workloads and see what are their data movement bottlenecks and see if they are more or less suitable for processing in memory, for example, or other techniques to alleviate data movements, right? The move methodology has different steps. We start from some target application. We start from the source code of the application that we want to analyze. And the very first step is to do an application profiling. In this application profiling, what we will normally do is defining a region of interest. That's why we need these hooks, ROI begin and ROI end, that define the part of the code that we want to analyze. This might be, I mean, you could do it for the entire application as well, but because applications have phases and different phases have different requirements, they have different access patterns, for example, it probably doesn't make sense to analyze the entire application as a whole, right? Because you're gonna get confused by the different memory access patterns and different computation patterns that different phases of the application have. So what makes more sense is to do some initial screening. You probably suspect where the application is wasting execution cycles from the memory access or spending too much energy due to memory access, and you can place the ROI begin and ROI end there, right? That's the part of the application that we are going to analyze. You could start doing the analysis with some profiler on a real system. There are good profilers such as Intel Vitium for Intel CPUs, but there are also like good profilers like Perf or GProf, and GPUs have their own profilers as well, such as NVIDIA Insight. These tools usually provide us with useful information that allow us to characterize applications, right? How many memory access they do, how much they hit or they miss in the different levels of the cache, etc. Right? So in some sense, with execution on a real system, or in some way with execution on a real system, we can characterize the workload and see how good or bad is in terms of data movement. But if we want to go deeper and go to a more comprehensive analysis, then the move methodology can be a pretty useful one. The move comes with a simulator, and with this simulator, it's possible to, first of all, obtain some memory traces that basically are the sequence of addresses that will be accessed over the execution of the program. You can extract these memory traces. That's why you see there load, store, load, store. You can extract these memory traces from the simulator. And with these memory traces, you can analyze the access patterns, right? And the first thing that we do with these traces is the locality-based analysis. You guys know how cache memories work. You know that cache memories are there to exploit locality. There are two different types of locality, right? A spatial locality and temporal locality. Spatial locality means that data, you have accessed data and you will continue accessing data that is spatially correlated, is near the data that you just accessed. When you have higher spatial locality, means that you tend to keep accessing data that resides nearby. You keep you tend to keep accessing data that is adjacent to previously accessed data. And then we have temporal locality as well, because programs are sometimes, well, they repeat computation, they have for loops, for example, they go again and again over certain values that are pretty useful, and they are reused, and that's the temporal locality. So that's one of the things that we do in this step 2, is analyzing spatial and temporal locality of these memory traces. If one application or the part of the application that we are analyzing has high spatial and temporal locality values, that means that the application or that part of the application can take advantage of the cache hierarchy of the CPU or the GPU, right? If these locality indices, let's say, or these locality markers are low, that means that we are not making good use of the cache hierarchy. So that means that we need to go to memory very frequently, right? So I'm giving you, let's say, mentioning some metrics that are useful to understand what are the memory access patterns of a particular workload. Then in the third step of the methodology, what we do is an scalability analysis. In this scalability analysis, what we do is, increasing the number of cores from 1 up to 256. And this way we see how the performance changes as we scale the amount of processing elements or the amount of cores. And this way, we also see how the exploitation of the bandwidth changes and the access to memory changes for different number of cores. And this gives us also a lot of insight on the specific memory bottleneck, if the application has or the code has any memory bottleneck. And using the metrics obtained from step 2 and from step 3, we can somehow use our classification. When you see here this high, low, even though, I mean, the picture is quite generic, but this high, low refers to a specific metrics that have been obtained either in this step or in this step. Metrics such as spatial locality, temporal locality, Mpki, that is the number of misses, cache misses per 1,000 instructions, per kilo instructions executed on the core, and metrics like that. So metrics that give you an idea of how is the memory access. And depending on whether the value of these metrics is high or low, we have this, let's say, classification tree that leads to 6 different categories of workloads, 6 different classes of memory bottlenecks. We may have a detailed lecture about the move later, but yeah, for now, this is should just serve as a short introduction. Here you can see the link to the paper. There are slides as well. There is the source code, is everything available, the simulator and the benchmark suite. There is a benchmark suite because we analyze a lot of workloads here. I don't know if maybe around 150 different applications that we analyze and classified, and in the end, well, we made them all available all together, even though those workloads are already existed from some programming frameworks, from existing benchmark suites, but now we provide them all together with the region of interest that we analyze in our work. So it can be good work to enable more studies related to processing in memory. The move simulator is indeed an improved version of a former simulator of our group, that is Ramulator PIM, that at the same time was based on a previous simulator that is still widely used for analysis of DRAM studies, that is Ramulator. Okay, so talking about workloads, I mentioned the workloads that come, the benchmarks that come with the move simulator. We have also created another set of benchmarks or workloads for processing in memory systems. In particular, these ones called PRIM benchmarks are for the UpMem PIM system. They are specific to one particular PIM system, but they can be for sure useful for later studies to improve that architecture, to propose software optimizations or compiler optimizations for this architecture. As you see, that it's a relatively varied set of workloads from different domains, like sparse or dense and sparse linear algebra, databases, data analytics, graph processing, etc. And all of these are also publicly available. We will talk about them for sure, because I think I'm going to give you a lecture, a specific lecture about the UpMem PIM architecture. That won't be hopefully next week. I think it will be the week after. We will see. And we will talk in detail about all these PRIM benchmarks. Anyway, if you are impatient, you can already check a former lecture. Okay, more examples of infrastructures that are needed for processing memory systems or to enable processing in memory systems. This one is NAPL. This one was machine learning based model for performance prediction of processing in memory systems. You guys know machine learning is pretty useful to make predictions, right? And there are many different machine learning models. Right? In this particular work, we used random forest because they showed good accuracy in the prediction. But yeah, basically is what this NAPL work does is extracting some basic characteristics of the workloads in terms of how many instructions they execute, how many memory accesses they have, data types that they use, etc. And that information, together with some information about the PIM architecture itself, are provided to the ML model, and the ML model will give you a prediction of the performance and also the energy consumption. This kind of work can be pretty useful, for example, if you want to evaluate PIM suitability, right? Is one particular workload good for PIM or is not good for PIM? Should I write code? Should I write PIM code for this workload and then offload and then see if I improve the performance? Or can I do something and analyze this PIM suitability before I spend time on writing the code for this specific course, right? For this specific PIM course. There is where this sort of performance prediction can be pretty useful, right? Evaluating PIM suitability in order to save time to developers. Another infrastructure that can be used for processing in memory is SoftNC. And we indeed talked about SoftNC yesterday, because this is the platform that compute DRAM authors used to evaluate row clone and ambit in real DRAM chips. And there are more simulators, many more. This one is also quite a good one, popular one, widely used. Is MQSim, is a simulator for SSD devices. And this one can, indeed, I think it has already been extended for processing near the storage. Right? So in the end, it's a simulator that simulates how an SSD works internally. So it makes sense to extend it to enable also some computation there. Okay. Yeah, we were talking about these applications, these infrastructures. We talk about benchmarks. We talk about ways of identifying when a workload can be suitable for processing in memory or not. And after identifying if a workload is suitable for processing in memory, what really makes sense is to evaluate it on a processing in memory system. And there are also multiple works, some of them from our group, that evaluate new applications and new algorithms and use cases for processing in memory systems. A good example is this one, this green filter, fast fit location filtering in DNA read mapping using processing in memory technologies. This is an accelerator, processing in memory accelerator for seed filtering. It is a way of filtering data in genome analysis before doing the sequence alignment process. You will learn more about this in later lectures probably, but as you may know, in genome sequence analysis, what we have to do, we have a bunch of reads that are coming from a particular individual, for example, they have generated, these reads are pieces of the genome of this individual. They have been generated by a sequencing machine, and these sequencing machines, unfortunately, don't give us the entire genome as a whole. They give us these small reads. So what we need to do if we want to analyze the genome of a person is first of all reconstruct the genome from the genome of this person from the reads. And to do so, we use a reference genome as the reference. This reference genome corresponds to several people, was created a few years back. I think that probably Mohammed Alser will give you a talk about this, a lecture about this, and you will learn exactly when this human reference genome was created. But yeah, there is this whole string that represents the human reference genome with the individual, with the small reads from a particular person. You can use the reference and find what's the right place of the individual reads. That's the sequence alignment process, right? And some of the cases, I mean, in principle, because the reads are pretty short, they can somehow fit in multiple places of the reference genome, and it's good to identify when it makes sense to try or not, right? And that's what we call the filtering step. There are different ways of doing filtering. In this paper, it's some seed filtering is the technique that is used. And this seed filtering is based on some bitmaps that can be very efficiently analyzed using memory. Read mapping is an approximate string matching problem. The sequence alignment itself is matching the reads to the reference. That's why we talk about approximate string matching. We also don't expect to have exact matches. That's why we talk about the approximate string matching, because in the end, the genome of a person is completely different from the genome, or very different from the genome of another person, right? And we are comparing them all to the same reference, so there will be some differences for sure. So alignment is currently the best method for determining the similarity between two strings, but it's expensive. So that's why it's good to have one filter before doing the alignment to reduce the number of required alignments. And that's the goal of this work was implementing this green filter using in-memory processing in 3-stack memory, and it showed a speed up of 3.7 times. GenAsem is also about approximate string matching, but this one, even though it could also be used for filtering, is used for the sequence alignment process. There are different algorithms to do sequence alignment. You might have heard of Needleman-Bunch or Smith-Waterman, are all algorithms, very popular ones that use dynamic programming techniques. GenAsem proposes a new algorithm that is pretty efficient and also comes with its own near memory accelerator. And as I said, I mentioned this work earlier as well. Probably you will learn more about it in a later lecture. Google Workloads are also a good example of applications that can get benefit from processing in memory, as we have already seen and analyzed. We also talk about
near data processing base or FPGA based near data processing. Remember that I mentioned FPGAs. I mentioned that they are shipped these days with high bandwidth memories, so you can have very high bandwidth access to data from the accelerator implemented on an FPGA. In this work in particular, we created a stencil accelerator for weather prediction modeling. You might know that weather prediction is done using pretty complex simulators that are usually executed in supercomputers. The workload, the weather prediction application that was used here employs a stencil computation very much. And even though stencils are quite regular and indeed there are techniques to improve the locality of accesses in stencils and make their computation faster for CPUs and for GPUs, but they are inherently memory-bound computation. So that's why if you can enjoy higher bandwidth, then that will be better, right? And that's what this narrow paper proposes, an accelerator for stencil computation for weather prediction modeling. This is another one, I already talked about it, about time series analysis. Again, we have to access a lot of data. It's mostly about comparing certain patterns that we want to find in the time series to the whole bunch of data that we have in the time series. Using a near data processing accelerator can be very, very beneficial for these applications as well. And what else? Well, summary of everything that we have covered yesterday and today. You can find it in this book chapter, but also can find in the shorter paper from Micro and the other one from IBM JRD. There is a challenge and opportunity for the future is creating fundamentally efficient, energy efficient and data-centric computing architectures that are also high performance and computing architectures with minimal data movement. You already know what are the things that need to enable to enable the adoption of processing in memory. We have discussed that as well, same as we discussed about the need for intelligent memory controllers. And you have seen how important memory controllers are as well in many of the processing in memory proposals that we have explained today and yesterday, where the role that they have on controlling how the operation, how the computation happens on the memory side. So we want to enable this paradigm shift. And recall, in computer architecture today, you can revolutionize the way computers are built if you understand both the hardware and the software and change each accordingly. You can invent new paradigms for computation, communication, and storage. A recommended book here is The Structure of Scientific Revolutions from Thomas Kuhn. In the pre-paradigm science, there was no clear consensus in the field. In normal science, there is a dominant theory that is used to explain and improve things, and exceptions are considered anomalies. And here we try to push for exceptions, right? Revolutionary science so re-examines the underlying assumptions. The fact that a computing system has been built the way it has been built until now, with memory on one side, processing capability on another side, and both connected through some communication channel, doesn't mean that things should be the same forever, right? The fact that memory has only been optimized for capacity or to store more and more data, same as storage itself, doesn't mean that they cannot perform computation in future computing systems. So that's why it's good to re-examine the underlying assumptions of the existing science. This is the picture of the book. Here you have another version. And the truth is that there are really people who believe that things can change, that try to revolutionize existing computing systems. A good example, existing example already, are the processing in DRAM architecture from the French startup AppMem. You already know this picture with two different CPUs or two dual socket CPU, DRAM DIMMs and PIM-enabled DIMMs in the same system. But that's just one startup. Also, major vendors are exploring processing or proposing processing in memory systems. We have talked here about FIMDRAM that is based on HBM2 memory. Remember how it's implemented. We have a PCU block or processing unit near every two memory banks. Another solution, and recall as well, or classification, right? Or two types of processing in memory systems, and the different ones that we consider there is a DIMM-based solution where some of the DIMMs are replaced with other DIMMs that have a small Fpga on them, and you can program them for different applications, for example, recommendation systems. This is a more recent proposal from another DRAM vendor, major DRAM vendor, SK Hynix, but is somehow similar to FIMDRAM because it also places processing units for machine learning and artificial intelligence near the memory banks. And remember how each of these processing units look with an array of multipliers, another tree, and some other interesting functionality. And the other example from Alibaba for recommender systems. So the truth is that even though there might be a mindset problem in industry and maybe even in people in academia, the truth is that processing in memory is becoming a reality. We have access to real world processing in memory systems, and we see how many other companies are prototyping and announcing their processing in memory systems. So yeah, with all of them can achieve what we really wanted, that is everlasting energy and much more performance. Again, fundamentally high performance and energy efficient computer architectures that are also low latency and compute with minimal data movement. Questions? You're too tired. Okay, well, I just have a few more slides for your own motivation, and also as concluding remarks. These are very beautiful slides from Professor Mutlu that are kind of inspiring as well. A quote from a famous architect who said, architecture should be based upon principle and not upon precedent. The architect who said that is this man here, he's Frank Lloyd Wright, and he applied this to his own work. Instead of creating something like this that is just based on precedent, he created something like this that is based on principle. And here you have another view of it. And overarching principle of his architecture is called organic architecture. It's a philosophy of architecture. So he created his designs, his buildings, following some principles. And that's what we are advocating for here in this course when creating computing systems. Your principles need to be very clear, creating architectures, computer architectures with minimal data movement, because data movement consumes execution cycles and consumes a lot of energy, and avoid the mindset of the computing system is already working this way because that's the precedent, and we should keep doing the same thing, right? So that's the idea that we are trying to convey in these lectures, and in particular with these final slides. Here you have another example. This will be a principle-based design, this ugly train station, and this is a principle design. It's pretty familiar to both of you, to all of you probably. And this is another principle design. This one is in Lisbon, but it's from the same architect. This one is in Valencia, in Spain, or this one is in New York. And the architect is this one, is Santiago Calatrava, who, by the way, studied at ETH. In his case, the overarching principle is different. It's not organic architecture, it's zoomorphic architecture, and he sticks this principle, and that's why he makes a difference in his designs and how he builds, how he designs his buildings. So what's the overarching principle for computing? Well, we can have many. I already mentioned computing with minimal data movement, but of course, trying to have computers that are very efficient, very sophisticated, same as the brain is, right? It's a very efficient machine that is also very low power. It consumes little amount of energy and that is able to do amazing things. So as concluding remarks, it's time to design principal system architectures to solve the memory problem, design complete systems to be balanced, high performance and energy efficient, data-centric or memory-centric. Memory doesn't need to be dumb. Memory can do useful things. And this way we will alleviate some of the bottlenecks at least. This can enable or can lead to orders of magnitude improvements, enable new applications and computing platforms, enable better understanding of nature, etc. Regardless of challenges in underlying technology and overlying problems and requirements, processing in memory can enable orders of magnitude improvements and new applications and computing systems. But we need a view over the compute stack across the entire computing stack, and design enabling systems. So change things in existing systems to enable this different paradigm or this new paradigm. So we need to revisit the entire stack and exploit good principles such as data-centric system design. All components can be intelligent, better communication across layers and better interfaces, better than worst case design, heterogeneity, flexibility, and adaptability. And we have just covered a few of these things, or started to cover a few of these things in these four first lectures. We will continue doing that in later lectures as well. If in doubt, if you are doubtful about processing in memory, for example, you can also think about other doubtful technologies, that they were emerging at some point. They were not very successful in the beginning. Some people, there probably was some pushback from people, different people from industry, etc. Good example of that are flash memories in solid state drives that they are widely used, ubiquitous in SSDs these days. And if you look at the timeline, the history of this NAND flash technology, it started very timidly. As you can see, there are some developments in the 60s, in the 70s, but not really so much. We don't see almost anything between 1970 and 1976. At some point, more developments start to appear much more frequently. And if you look at the most recent years, there is still a lot of innovations. And you can also see, probably the numbers at the top relate to the amount of money that is made every year with a flash memory, right? And probably in the beginning was nothing, but today they are everywhere. They are in our cell phones, they are in our laptops, and essentially in any computing system. Okay, yeah, just to close the slide deck, to close the lecture, recall our book chapter about processing in memory, and also the papers micro and IBM GRD. So this is all from my side. We still have 5 minutes if you have questions, or I don't know if you want to take a nap. Yeah, what's the question?
Hello.
Hello, I can hear you.
So I have 2 questions. First is, like, from your point of view, is PIN an accelerator or just memory? Because like we can tolerate higher cost for accelerators, but for memory it's very cost intensive, like cost sensitive. So that's my question.
Yeah, that's a good question, actually. I think that the first answer relates to the specific system that you are talking about. In a system like ABMEM, for example, where the PIM DIMMs are not working as main memory, at least in the current ABMEM system, you can see them as an accelerator, right? Most of the, well, maybe not most, but let's say that you still have a CPU that has its main memory as in a traditional system, and now you can have another accelerator that is based on processing in memory. It's memory with some processing cores. But anyway, over the course of this lecture and yesterday's lecture, we have been talking all the time, and there are even some slides that say memory is your accelerator, right? So I don't think that's important. You talk about cost, and that's important for sure. We don't want to make our systems much more expensive, but the cost of things is not only the cost of buying the thing, you know? The cost of my cell phone is not only go to the shop and pay some money and get my cell phone, because after that, I have to pay, for example, a subscription to a company, right? A telephony company that gives me the service. And I may need additional accessories, such as this case or some protector and so on. So all of that makes what is called the total cost of ownership. If you buy a laptop, it's not only pay for the laptop, you'll have to pay for the applications, you'll have to pay for the electricity, you'll probably have to pay for possible repairs, you'll have to pay for a bag. All of that is the total cost of ownership. If you have a system with processing in memory capabilities, the memory itself, and even if this processing in memory, right, this PIM memory replaces conventional DIMMs completely, right? You will have memory that is more expensive because it provides additional features, but you will be saving money because you can execute workloads much faster and in a more energy efficient manner. And that will make you save money. So it's indeed a good question, because when it comes to evaluating these systems or also comparing PIM systems with other accelerators like GPUs, it's something important to take into account. Yes.
So I have another question about the technology itself. So I think things like DRAM has a different technology than CPUs, right? So like looking at the UPMM system, it has technology that like 14 or even more than 20 nanometers.
Mm-hmm.
Whereas for CPU and GPU, we are approaching like 5 nanometers.
Mm-hmm.
So do you think this difference is inherent, or it's just because of a difference between a startup and a very large company?
Yeah, I think so. Regarding the technology node, I think it's more related to how big the company is. There is no reason why you could not fabricate the ABMEM DIMMs at the newer technology node. There's no reason for that. Fabricating logic, creating logic using DRAM technology, as we have said a couple of times, has its own challenges because of the number of layers you have, because of the type of transistors, but that's a different discussion, right? Processing in memory can also be enabled with 3D stack memories. There you could really have layers that are CMOS layers, and they could have much faster transistors as well, right? And solve some of the issues. But yeah, I think that, yeah, of course, ABMEM is a startup, and they have to face some limitations that bigger companies don't have, probably. Relates as well to the total cost of ownership, right? If you have a very small company and you just fabricate a few hundreds or a few thousand DIMMs every year, the cost of these DIMMs will be higher than if you fabricate millions. Okay, yeah. Okay, thank you very much for the questions. Anything else? No? Okay, then I think we are done. We are 1 minute over time. So yeah, thank you very much for your attention. I hope you have a nice weekend. And I think next week you will have the chance to meet Professor Mutlu in person.